The second part of our discussion of centers of mass has to do with what are called planar lamina, which is a fancy word for thin plate of material. So I'm going to imagine I've got some thin plate of material. Maybe it's made out of metal or some other substance, and I want to find the center of mass. As a simplifying assumption, we assume that the mass density, which we'll call rho, is a constant. We will get away from this in Calculus 3 when we study multiple integration. In general, the pattern that we're going to follow is the same pattern that we've done before. We'll take the planar lamina and chop it up into a bunch of much smaller pieces. I'm going to look at one of these chunks. It's going to have area delta capital AI, and I want to think about the contributions that this chunk is going to make to the moments about the y-axis and about the x-axis. Since I'm assuming that the mass density is uniform, the mass of this chunk that I'm looking at is just going to be the mass density times the area of the chunk. The total mass is the mass density times the area of the chunks, and then we add up all the chunks. This is going to be the mass density times the total area of the region, which in some cases we do know how to calculate. This little piece of my region is going to have a contribution to the moment about the y-axis as the mass times the distance out from the y-axis, either in the plus or minus sense. The mass is the mass density rho times the area, so I just have to multiply by the x-coordinate of the chunk, then add up all such things, and then in some sense take the limit as the size of the chunk tends to 0. As with arc length, it isn't immediately clear what I should do about turning that into an integral. What we'll do is we'll have a special case where things are easier to think about. In the same way, if I want to find the moment about the x-axis, I multiply the mass by the distance from the x-axis, which is given by the y-coordinate. And like before, I have the same problem. I don't immediately know how to turn this limit of sum into the sort of integral that we've done previously. We're going to call a region vertically simple if it's bounded on one side by the vertical line where x is a, on the other side, vertical line x equal b, and bounded above and below by graphs of functions. I'll call the function above f, and I'll call the function below g. The reason that this is called vertically simple is that you can imagine slicing it up into vertical rectangles. What we'll do is we'll figure out the contribution to each of the moments from one of these rectangles, add them all up, and then we'll be able to see how to convert this into an ordinary integral. The area of such a thing is the horizontal delta xi, as we've done before. The vertical is the difference between f of xi and g of xi, which makes us think all the way back to area between curves, which is why we started looking at that. The mass of this vertical rectangle is going to be the mass density rho times this area. So the bit of the moment about the y-axis that comes from that one particular vertical rectangle we were looking at is the mass density times x number I times the area, which we have already previously stated. The xi is the distance from the y-axis to this vertical strip, The reason that this is not so complicated is I've got a very skinny vertical strip, and I can think of its x coordinates as being all more or less the same. Add up all such things, and then take the limit as the delta xi's tends to 0. And now this is exactly the kind of setup we've had before for integrals. The limit of the sum turns into an integral sign. The delta xi's turn into dx. This is a constant factor, so I'll just write it down. And everything that had xi in it in the Riemann sum just becomes x. So the moment about the y-axis is given by this integral. Since we already know the mass, this means we can go ahead and calculate the x-coordinate of the center of mass. The mass of the region is the mass density times the area of the region, which we know how to do. We've figured out the moment about the y-axis, so x bar, the x-coordinate of the center of mass, is given by moment about the y-axis divided by total mass. If you look at that formula, there's a factor of rho, the mass density, upstairs and also downstairs, so the mass density cancels out and ends up not mattering. I have now a formula for the x-coordinate of the center of mass. I'm still thinking about that same vertical rectangle. Now I want to find the moment about the y-axis. Well, excuse me, I know the moment about the y-axis. That was easy-ish because these vertical strips more or less had a common x-coordinate. Now I've got a problem though. If I'm trying to calculate the moment of this vertical strip about the x-axis, it's not true that I have a common y-coordinate that I can describe the strip. Even if the delta x becomes very small, there is a wide variety of y values. So I'm going to have to figure out the moment about the x-axis of this vertical strip some way or the other, and then add up all such contributions and take the limit. So we're just thinking about the contribution to the moment about the x-axis of that same vertical strip that we were talking about. What we'll do is a second layer of integration. I'm going to carve the vertical rectangle up into a bunch of much smaller rectangles, each one of which will have horizontal width delta xi, and one of them, for example, will have a vertical height delta y, number j. The area of one of these little rectangles is delta xi times delta yj. The distance of this rectangle from the x-axis is its y-coordinate. And since I'm looking at sub-rectangle number j, I'll call that y-coordinate y number j. So the contribution to the moment about the x-axis, just due to this little rectangle here, is going to be the mass density times the area of that little rectangle times how far out from the x-axis it is, which is given by the y-coordinate yj. I'm still thinking about the contribution to m sub x due to that one vertical strip, and I'm going to calculate it by adding up the contributions of all of these smaller rectangles. We have to keep straight what we're doing here. We're looking at a particular vertical rectangle, so the xi is a constant and the delta xi is a constant. It's the y-coordinate and the delta y's that vary now. So I add up all the contributions. mass density times area is mass times how far out I am from the x-axis, you could group this by factoring out the things that within this vertical strip are being treated as constants. To get the contribution of this one vertical strip to the moment about the x-axis, I have to take the limit as all of the delta y's go to 0. So I have this limit, and within the context of working with one single vertical strip, this trailing factor here is a constant. Later it won't be, but we're just thinking about one particular vertical rectangle right now. That last limit of sum is the definition of an integral. It's the integral of y with respect to y from the smallest y value involved to the biggest y value. The smallest y value is g evaluated at xi. The biggest one is f evaluated at xi. And the quantity inside the parentheses is now an integral that we know how to do. If y is the variable, which it is in that inside integral, an antiderivative is 1/2 times y squared. I have to put y equal f of xi, y equal g of xi into that antiderivative and subtract, not forgetting to include my factor, which is basically a constant at the moment. You can write the result several different ways using the difference of squares formula. A squared minus b squared is a plus b times a minus b, and grouping the f of xi plus g of xi and the 1/2 together, the moment about the x-axis that goes with that one vertical strip is given by this formula. Now, what I'll have to do is add up all of these things, add up all the contributions for vertical strips in my vertically simple region, and then take the limit finally as delta xi tends to 0, and that'll give me my formula for the moment about the x-axis. So finally, after doing all the simplifying and taking the limits and pulling the constant factor of mass density out front, the moment about the x-axis for this vertically simple region is given by an integral, but it's more complicated than the other one. I'm going to have the mass density times the integral from a to b with respect to x. This factor, f of x minus g of x, is no surprise to us. It's basically the area after you get done multiplying by the delta x, and this is the additional factor I have to put in order to calculate m sub x. Your book just states that this is obviously what you should do. It is not obvious that you should do this. So this is why I've gone through the argument that shows this is the thing that you should do. Putting all of our pieces together, we calculate the integral that we just stated divided by the area, having canceled out the constant mass density. The y-coordinate of the center of mass is given by this formula. This looks just like the formula for the x-coordinate, except you have this factor instead of an x. So summarizing everything we've figured out so far, this is how we'll calculate the x-coordinate of the center of mass, and this is how we'll do the y-coordinate. As an example, think about the region in the plane that's between the graphs of y equals x squared plus 1 and y equal x. starting at x equal 1, ending at x equal 3, I've got to calculate the mass. Now, strictly speaking, if I wanted to be picky about it, I should include the mass density as a factor, but we know it's going to cancel out anyway, so I'm just going to omit it. The area between the two curves is the integral from 1 to 3 of the upstairs curve minus the downstairs curve. And I actually worked this out by hand. It turns out to be 6 2/3, 6.6 repeating. This number is going to be the bottom of the fraction for x bar and for y bar. The moment about the y-axis is that same integral that we calculated for the mass, also known as the area for us, except we have an additional factor of x. So I could do this by hand. I could multiply it out and find the antiderivative of x cubed plus x minus x squared, put in 1 and 3 and subtract, but I was feeling lazy, so I hauled my calculator out and did it with the numerical integrator. The moment about the y-axis is 15 1/3. So this means the x-coordinate of the center of mass is the moment about the y-axis divided by the mass. We know both of those numbers now, and the fraction works out to be 2.3. This is the x-coordinate of the center of mass. The y-coordinate of the center of mass is the moment about the x-axis divided by the mass. We've already canceled the row out, and what remains is 6.6 repeating. The top of the fraction is the same as the integral that I did for the moment about the y-axis, except this factor is not x, it's the average of f of x and g of x. Once again, I got the calculator out and did it numerically. The moment about the x-axis is 29.5 and then a bunch of repeating 3's. The y-coordinate of the center of mass is 29.8 and a bunch of 3's divided by 6.6 repeating, which works out to be 4.4. So we now know the x and y coordinates of the center of mass. Unlike my previous pictures, which were just drawn to give me an idea of what's going on, I made some effort to draw this one to scale. When x is 2.3 repeating, I'm on the vertical dotted line. When x is 4.4, when y is 4.4, that is, I'm on this horizontal line. The center of mass is right there. It's at x equals 2.3 repeating, y equal 4.4. If you were to cut a shape out of this, if you were to cut a shape out of balsa wood in this shape, and you wanted to find the point where it would balance if you put it on a fulcrum, the place would be right there. If you have a horizontally simple region, that's a region bounded by y equals c and y equals d above and below, and on the sides, instead of y being a function of x, x will be a function of y. So this will be x equals f of y, and this is x equals g of y. You can go through the exact same argument that we did for the vertically simple case. I won't make you suffer through that. The conclusion is x bar will be given by this formula, and y bar will be given by this formula. If you look at these formulas, they are basically the same as the ones we got for the vertically simple region, except every place you had an x, you now have a y, and vice versa. The interested person can work through the details but this is what you end up with. This is the last topic we're going to talk about in the chapter on applications of integrals. Coming soon will be methods of integration, which is the next chapter. It's frequently the case that people lose sight of what we're doing. We want to be able to integrate more things than we can integrate now because of the applications, the area between curves, the arc lengths and volumes and work, and now centers of mass. So we will talk about that very soon now. In the meantime, I hope everyone is doing well. We'll talk again soon.